All right. Um, as you all know, you just turned in homework 5. As I had said at the start of the class, I, want you to work on your presentations now. So there isn't going to be any more mandatory homework for the rest of the course. I don't know why I'm standing here with a piece of chalk because I'm not going to write anything, but I plan to post on Crowdmark a bonus assignment, which is just like a list of problems in Vakil I think it would be good to work on. And you are free to do that or not do that. Um, I'm putting it on Crowdmark so you can submit things, which I will in an opaque way that I don't feel like explaining because I honestly haven't decided. Somehow incorporate that into extra credit if you put things there. Um, yeah, I mean it when I say it's a bonus, so it is purely optional, but I thought, could be useful to do some problems on, you know, the chapters we covered in the last couple of weeks and future ones. Yeah. I mean, I will set a sometime during finals. Right. It needs to be soon enough that I can look at it before I have to sign final grades. So it can't like quite be like literally the end of finals period, but it will be in the finals period. All right. All right. Cool. Any other questions? All right. So as I said last time, we really need to get moving. Get through some of the more important topics. So today, I'm moving on to the next chapter, and we're going to talk about locally free sheaves. All right. So this is the algebraic geometry version of a vector bundle. So let me just remind you a tiny bit about vector bundles in differential geometry. So smooth vector bundles, what does that mean? So that means I have a space E and a base B such that the fibers are vector spaces. And this is locally trivial, locally isomorphic to a trivial vector bundle. What does that explicitly mean? Right, we've been doing a lot of stuff about things being local on the base. This is a sort of relative property. It means there exists an open cover, UIs on B, I'll call this map pi, such that if I look at pi inverse of UI mapping to U, right, we're now sort of thinking about everything in a more relative way, right? So I'm thinking about a property of this map. This map is isomorphic to Rn, or I could use Cn if I preferred a complex vector bundle. But these two maps are isomorphic. And of course, this isomorphism has to be a vector space isomorphism on each fiber. I was a bit lazy here about saying how these vector space structures are supposed to be compatible, but this isomorphism takes care of that, right? The fact that I have an isomorphism here, which is a vector space isomorphism on every fiber, sort of forces the vector space structures here to vary smoothly. All right. One kind of common way to think about this is I can give this guy a name. phi, right? And then if I wanted to think about how could I kind of build this vector bundle out of trivial vector bundles, well, phi only makes sense once I've already constructed my E. But if I look over ui intersect uj, well, I have phi inverse of that. And then I have two trivializations here, right? I have phi mapping to ui uj times Rn, and I have Cj mapping also to ui uj times Rn. And I can, these are all with the projection, I can compose these. So Vacchio calls this Tij. There's sort of a horrible left-right mismatch here. So, and I'm just following Vacchio's notation, the transition map from the trivialization for I to the trivialization for J. So these satisfy the composition property that Tij and then compose. I keep trying to make this a J. Jk is equal to Tik, which is kind of horrible, but it's all the fault of whoever wrote fx the first time. Obviously, composition should go the other way, but that's not the world we live in. So we just have to accept that. All right. So we often think about these bundles in terms of transition functions, right? What kind of map is this? Well, it's the identity on the first component. And then on the second component, restricted to each fiber, it's a linear isomorphism, right? So Tij, when I apply it to some uv, so this is in the intersection and this is in Rn, I have to get, well, the same u, and then Av, where what is A? It's a linear isomorphism from Rn to itself, also known as an invertible matrix. So this map, people often will think of this really as being a map from ui uj into gln. Yeah.
Should Tij be?
I think I did this right. Certainly what I have in my notes is that Tij is this map, right? So this is telling me I want phi j composed with phi inverse. This is ek phi j inverse. So at least what I've written here is consistent. And that's the best I can hope for, because, this is somehow one of these things where no matter what you decide, somewhere you will encounter something where you're like, oh, why did I choose this notation? This is horrible. But if you fix that, you'll create some other problem somewhere else. Okay. And I'll note here, there's really nothing special about vector bundles, right? There's sort of a general theory of fiber bundles that works almost exactly the same, where you say, I'm going to have something locally trivial, and you say, what are the structure preserving isomorphisms of your fiber? So what you always have is you have a fiber, and then you have a structure group acting on that fiber, and you say, I'm going to choose transition functions in that structure group. Just this is the one that's relevant for us. Yes. Yeah, I mean, right. People would often say that in terms of there being a smooth manifold structure on E, and everything here being smooth, in particular, the phi being an isomorphism a smooth isomorphism, right? I was being a little vague about what category I want to work in because I can do all this stuff smoothly or topologically, sort of doesn't change much. But you're right that, this map has to be sort of well defined in the right category. It has to. So here, you can think about going the other way. You can think about starting with these maps and then producing a vector bundle by gluing. As long as I have this condition. And exactly, yes. Right. I mean, it's basically if and only, right? E is a smooth manifold with these trivializations being smooth if and only if I choose my Tij smooth. All right, great. So now I want to think about this in a more algebraic geometry type context. So how would I switch from thinking about this in terms of smooth manifolds to thinking about my smooth manifolds as ringed spaces? I would say, given E, there exists a sheaf F sub E, where what is F sub E of U? It's the sections of E on U. Right, so it's maps from U into E such that when I compose with the projection, I get the identity. So in particular, if E is trivial, if E is B times Rn, then this is just C gamma of B. Right? A smooth function valued in R is the same thing as a section of the trivial bundle. More generally, if E is a trivial bundle, but of higher rank, what do I get? I get this guy direct sum n times. Right? I choose n smooth functions to be my n coordinates. Okay. So what kind of thing is this? Of course, it's a sheaf of abelian groups, but it's a sheaf of abelian groups with an extra structure. Because the fibers of this are vector spaces, I can do scalar multiplication on them. So I can multiply one of these by a smooth function and get a new such section. Yeah. Oh, yeah, obviously here I mean smooth. Again, you could do this in all these different categories, right? I could be doing everything in the topological category, and the point would be roughly the same. B is smooth, E is smooth. I know what a smooth map between two smooth manifolds is. Right? I mean, it just means when I apply this isomorphism to get, right, any section here, I can glue as sections on the UIs, and I know what a smooth section of this trivial bundle is. But that's just sort of translating what the definition of a smooth map is, right? The point is these guys give me an atlas of E, and I can test whether a function is smooth by restricting it to an atlas. All right, cool. So more generally, right, this FE is a C of X That's the infinity of B module. But it has an important special property, right? When I restrict to an open cover, I get a trivial vector bundle. So this guy, it might not globally be a free module, but it's locally free. So when I take this FE and I restrict it to the open set UI, then it's isomorphic to C infinity UI, take the direct sum n times. And that isomorphism just comes from applying this VI. Right? That exactly tells me how to take a section of this guy over UI and think of that as n smooth functions. All right, cool. So this property of local triviality of the vector bundle, when I translate it into this ring spaces language, becomes local freeness of the module. And now I say, oh, well, there's nothing special about smooth manifolds. If I have any ring space, I can think about locally free things. So for any ring space, a locally free Vex module Vex module, which is locally free. Such that, and I take f of I and I restrict it, or sorry, f restricted to ui, that becomes isomorphic to n copies of the structure sheaf. And one reason to think about this smooth case is hopefully most of you know that there are non-trivial vector bundles, right? For example, there are lots of manifolds whose tangent bundles are not trivial. So that means you know some examples of locally free sheaves which are not just globally free. There's sort of some global problem. Yes. So in good situations, think you might need Noetherian for that. Right. In order to do that, basically what you need is Nakayama's lemma. So I think if you take a general ring space, probably you can cook up some weird example where it doesn't work. But yes, on good schemes, everything will be fine. Yeah, and let me just a general announcement to make my life easier. From now on, all schemes are locally Noetherian. So in particular, right, there's this notion of finite type or finitely presented sheaves, and that as long as you're locally Noetherian, that's the same as coherent. We'll say coherent, if you read the section of Fakio, he'll sometimes say, for finitely presented sheaves, yada, yada, for finite type sheaves, yada, yada. I'm just going to simplify my life, always work with things that are locally Noetherian, and then I won't get into trouble. All right, this number n is called the rank of F. An important special case is if the rank of is 1, then we will call this guy an invertible sheaf. Or you will often hear line bundle. All right, this means that when I look locally, this guy looks like a copy of the structure sheaf itself. Yeah. Well, again, this is one of these points where, no, I don't think I need Noetherian for that. Because if you look at the overlap, that would tell you that two copies, the two free modules were isomorphic, and over a commutative ring, two isomorphic free modules have the same rank. Oh, that's true. Yes, sorry. You're absolutely right that this is only well defined. Yeah, that this is not uniquely defined for a disconnected scheme. You're right. Sorry, I should have mentioned that. So let me just say well defined if connected. Yes, I mean, definitely the sort of thing you might want to do sometimes is consider a sheaf which has one rank on one component and connected component, a different rank on another one. You could have connected components of different dimensions. And if you're smooth, you'll have a well-defined like tangent bundle, which is a locally free sheaf, and it could have different ranks on different components. Those different smooth components have different dimensions. All right. So let's talk about some examples. As line bundles, we actually do know some interesting examples of. I mean, first of all, we mentioned so a locally principal ideal and A. So that's an ideal I such that if I localize at any prime, that's isomorphic to the ring itself. Gives an invertible sheaf. So you'll often hear a module that satisfies this called an invertible module. That's a module whose corresponding sheaf is an invertible sheaf. It's locally free of rank 1. I twiddle spec A. And we know that there are non-trivial examples of these. For example, if you take a dedicant domain and any non-principal ID. If I look at spec of z adjoining square root of -5, right? The ideal generated by square root of -5 Q2 gives me an invertible sheaf on this affine scheme which is not trivial. It's not just a copy of the structure sheaf. It's some different, interesting line bundle. All right, more general. If I have a scheme X and I have in here an effective Cartier divisor, so this is the sort of non-affine analog of an invertible, a locally principal ideal. So this is a subscheme, which locally looks like it's cut out by a single equation. So when I restrict it to an affine subset, I get a locally principal ideal. Then the ideal sheaf Y is locally free. And you might think that's a very small generalization of this guy, but of course, this is something we can do on non-affine schemes in an interesting way. So, for example, on P1, a single point gives me an effective Cartier divisor. Say, so there's a locally free sheaf, which I could think of as a subsheaf of the structure sheaf on P1, which is given by its sections are sections over that same open set, but they have to vanish at O10. So this is called O of -1. So this is a non-trivial line bundle on P1. All right. Yeah. Mm-hmm. I mean, you just take smooth functions, right? That's the right analog for smooth things. All right, so these guys are going to be very important later, but we'll come to them some other time. Maybe I should say more generally. Right on Cn, I have a subscheme called V of x0, or I could take V of any of the other x's. The ideal sheaf of this is called -1. Right? So more generally, I could take any homogeneous polynomial here and look at its zero set. And I would get other line bundles here, and probably the next thing we should talk about is how all these guys are related, how you can get new locally free sheaves from old ones. So there are a bunch of natural operations. Basically, any reasonable operation you can do on vector bundles or on vector spaces, you can do on locally free sheaves and get a reasonable answer. So in particular, you can apply what's often called sheaf hom. So this is a little confusing because, of course, coherent sheaves are a category, and I can look at hom between two locally free sheaves in that category. This is instead what's called an internal hom, where I'm taking two objects and getting a new object in the same category, which sort of corresponds to hom between them. So I'm going to use hom underline. In printing, you would use sort of scripty characters for the hom, but it's too hard for me to consistently do that on the board. So I'm just going to use underline. So what is this? We actually have to be like a tiny bit careful about what this means, because it's tempting to write f view f g, g of u, right? But that's not a sheet, right? There's no guarantee that you can, that this is even a pre-sheet, that you can restrict one of these. So this is correct on small enough open sets. So there are various things you could do to kind of make this work. Maybe the easiest one is to say, for u affine, it's between the sections. And then for other u's, it's whatever the sheaf condition tells you to glue together. So I'm using the affine open sets as a base. Now, this sheaf on a base. Now glue. So a good example of this would be, what is hom from -1 to O? Right? Globally, this has no sections, and this has sections which are just constants. Right, did I do this right? Wait a second, I had really convinced my... Yes, okay, great. Right, yes, good. You always have to get the sign here right. There's also an O of 1. I was pretty sure I had the sign right, but I was worried for a moment there. Okay, so if I take global sections on P1 of O, then what do I get? I get just the constant functions. I'm working with P1 over some field, etc. Well, none of these vanish at this point. So none of these are in the ideal, right? Constant functions are in the ideal. Your vanishing set is empty. So if I took O of -1, P1 of K, now you start to see why people write gamma P1 O of -1. And that's just 0. So you might say, oh, obviously there are no homs from here to here. All the homs are 0, right? But if I take the hom sheaf, obviously it's not 0, right? So you can easily check here, right? If I restrict to open sets where these guys are trivial, you can immediately see this is locally free of rank rank of F times rank of G. So this is again a line bundle. It's what we call O of 1. Once we define this, there are some other useful operations we can define. So a common thing people want to think about is the dual locally free sheaf. And this is defined as underline from this guy to the trivial guy. So right, I could rewrite this as if I take O of -1 and take the dual of that, I get O of 1. For now, that's the definition of O of 1. And you can check, it's relevant here, if I take the sections of O of 1, that's actually two-dimensional. So in particular, there's obviously an inclusion map. So we can tell it's not 0. There's actually a two-dimensional space of sections. Sort of correspond to, you can think of this canonically as the span of x0 and x1. So this question of how do I interpret what x0 and x1 are finds an answer in terms of line bundles. I can interpret them as sections of this guy. We'll discuss other ways of thinking about these later. So there are other nice approaches. And furthermore, I can also consider the tensor product. And you guys already did a homework about how to think about this tensor product. This, at least, if I interpret it naively, is a pre-sheaf, and but then I still have to sheafify. So sort of all of these things, it's always you do it sort of locally on a small open sets, and then you sheafify to get things to behave right globally. And one useful thing to note is I can interpret the tensor product of the dual and F. And the way I check all of these is, well, I always can construct a map one way or the other, and then I restrict to small enough open sets where everything is free, and all of these are true for free modules. Cool. So here, this guy has the same rank as E, right? This is taking the dual vector space of every fiber, essentially. And this product is also the rank of this tensor product. And I'll just mention here, all these operations work for all coherent sheaves, right? I'm doing stuff that makes sense for any module. But of course, they won't be as well behaved. In particular, I even have to be a tiny bit careful about getting quasi-coherentness here. But let's just say for coherent sheaves, all of these things are sort of completely well defined. There's sort of some issue about like this guy's infinitely generated, yada yada yada. But if everything is finitely generated, then life is easy. And one more operation that got mentioned, I mean, I can also take symmetric and wedge powers. So in particular, the top wedge power of a coherent sheaf is very nice because it's a line bundle. So this is a common way of constructing line bundles to take this guy. Yeah. Yes, you would call this the determinant bundle. I mean, the way I would do the wedge powers is, I mean, I would just define this, right? I would define the operation on free modules of look at the wedges and then like mod out by y equals minus yx, right? Um, that's the same as sort of thinking about taking the dual and taking alternating linear maps. So you have to be like a tiny bit careful in characteristic P. Um, but yeah, I mean, right, anything that works with vector spaces, I can just do with this. So like any description of top wedge power that works for vector spaces. So I mean, I think one way to say what you're saying is you can think about it as volume forms on the dual. But I mean, you can also just think about taking the rank f-fold tensor product and then taking the quotient of that, sort of all of these relations. Yeah. Mhm. Mhm. It's exactly the same. Right there, you can take the wedge power of a module, which somehow, and all I'm doing is sort of that doing the wedge power free modules behaves like you would expect it to based on taking the wedge powers of the fibers, right? Like, yeah. I mean, all of these things, right? If you're thinking about the espace-Hatal, you can do them on the stalks and then say like, oh, actually now I'm going to take, sort of sections of this sheaf I built with the stalks. That's another option. That's kind of the closest thing to the idea of doing it fiber-wise. All right, indeed. That's a good introduction to what I was about to say, which is one of the things we often want to do is to think about the stalks. If I take f sub p, this is the stalk. This is a O of xp module, obviously free if f is locally free. And I'll note here, right, a useful fact to know is that for a Noetherian local ring, all projected modules are free. So it is actually enough. It's equivalent to saying that this is projective. Right, and I also will often want to consider the fiber, right, F with a revert and then P. That's take the stock and mod out by the maximal ideal. That's this guy. So the way you should think about this stock, this is germs of sections. It's like having the Taylor expansion of a section at that point. Whereas this corresponds to the actual fiber of the vector bundle. So this is a K of P vector space, finite dimensional. F is coherent. Right, so I'm sort of not being super consistent. I don't want to just assume that F is a locally free module the whole time, because actually it's sort of relevant that you can do all this stuff with any coherent sheaf. You just might not get a free module, right? You'll still get a module over the stock. It just might not be free. In fact, we can understand things very well in terms of these stocks. In particular, it's very useful to remember that we have Nakayama's lemma. So what Nakayama's lemma says when you think about it geometrically, this says if I have U and a point in U, so this is open, and here I have a point, and I have A1 up through AN sections of F over U, such that A1 through AN restricted to P span this fiber. Then, well, I can take these guys and look at their elements of the stalk, and they generate the stalk. But more generally, right, I can look at the subsheaf they generate. That sheaf maps surjectively at the point P. And so its co-kernel is 0 on some open neighborhood of P. So I can even more generally say there exists some possibly smaller open inside U such that A1 restricted to V through N restricted to V generate. So checking that these guys span the fiber is enough to check that they generate the sheaf in some neighborhood of the point. That's what Nakayama's lemma tells us. Yeah. Sure. Yeah. Indeed, one sort of context in which this is useful to think about is when this gives us a trivialization. So consequences. So F is locally free if and only if, let me say F here, coherent. Of course, I'm always assuming that I'm locally Noetherian. If and only if this stalk is free, which is equivalent to saying projective, for all P. Another useful characterization that comes out of this, that this guy is locally free if and only if. So I can look at this function of P, which is look at this fiber and look at its dimension. So for a general coherent sheaf, that could be jumping all over the place. But if I'm locally free, of course, it's constant, or I should say locally constant. So constant unconnected components. So more generally, this function is upper semi-continuous. And this sort of comes immediately out of Nakayama's lemma, right? What this is telling me is if I have a basis for this fiber, those elements have to generate over some open set. So in particular, they have to generate at any genericization of my point. And so the dimension can only drop. So a very common thing you'll use that this is kind of the geometric incarnation of is if M is finitely generated over R local, then M is free if and only M. The dimension of M mod the maximal ideal is equal to the dimension of M tensored with the fraction field. So this is the dimension of the fiber at the generic point. This is the dimension of the fiber at a closed point. So you can sort of detect freeness by whether those change. And probably I'm out of time. Oh, yes, I'm way out of time. All right. Yeah. The dimension over the fraction field. Right. This is dimension over the residue field. This is dimension of the fraction field. So for a free module, those will both be equal to the rank. And if you're not a free module, then this will be bigger. You'll have some generators which don't satisfy a relation in here, which do satisfy a relation over the fraction field. Why is this a consequence of that? Of Nakayama's law? This? Because I say as I'm erasing it, because we're really low on time. The other class is going to come in any minute now. Well, you pick a basis here, and then you think about the map of the free module onto M induced by that basis, right? And then this tells you that map is an isomorphism at the generic point, so it's an isomorphism everywhere.